Imagine a train, like weighing over 100,000 pounds.
Yeah, a massive piece of machinery.
Right. But it's floating entirely in thin air. And it's traveling at, I don't know, 300 miles per hour. And it is touching absolutely nothing.
No wheels.
Exactly. No wheels on a track, no engine burning jet fuel. It's just this massive metal tube gliding silently through space.
I mean, it sounds like literal magic.
Or at least really bad science fiction.
Yeah.
But it's not. It is happening right now in the real world. And it's entirely the result of this microscopic, completely invisible architecture that we interact with every single day.
It really is one of the great paradoxes of modern life, you know? We rely entirely on these classical mechanics we can see and touch.
Like pushing a door open, right?
Yeah, or dropping a glass and watching it shatter on the floor. But the absolute cutting edge of our civilization is powered by forces that are completely invisible to the human eye.
And that invisible landscape is exactly where we are venturing today. So welcome to you, our listener, our resident learner. We are so glad you're here because we have a custom deep dive queued up just for you.
We certainly do.
Today, we are looking at a highly concentrated source document. It's titled Principles of Magnetic Domains and Electric Currents. Now, when I first looked at your notes for this, I was actually struck by how brief they are.
They are very brief.
Yeah, we're looking at just 3 short excerpts from a set of physics standards. It's PS.PHY.5, 5.1, and 5.2.
Just a few sentences, really. But they actually outline a very rigorous 3-part framework.
Right.
It's a framework for deconstructing one of the most fundamental forces in the universe, which is electromagnetism.
Exactly. Our mission today isn't just to read you a syllabus. We are going to use this framework to kind of rip the lid off the black boxes of our daily technology.
From those floating maglev trains to the speakers in your headphones.
Yeah, we're going to unpack the actual physics of how this stuff works. So, okay, let's unpack this, starting with the very first directive, the anchor.
Right. Standard PS.PHY.5. The text simply says, explain the concept of magnetism.
And I have to pause right there because explain the concept sounds deceptively simple.
It does.
On a casual read, you might think, sure, I know what a magnet is. It's the thing holding up my grocery list on the refrigerator.
Right, the everyday experience of it.
But the standard doesn't say identify a magnet. It explicitly demands we explain the underlying concept. So, is there a fundamental difference between knowing what a magnet does and being able to explain the concept?
Oh, there is a massive difference. What's fascinating here is that recognizing a magnet's behavior is really just observation.
You see the metal stick to the fridge.
Exactly, you observe the phenomenon. But explaining the concept means articulating the invisible mechanics behind it.
Okay.
Magnetism at its core is a force of attraction or repulsion that acts at a distance. It's mediated by magnetic fields.
Mediated by magnetic fields.
Right, but to truly explain it, you have to answer the ultimate question. Where does that field come from in the first place?
Right. Because you look at a piece of iron and it just looks like a dead piece of metal. It's just sitting there.
Right.
So what is actually generating that force?
Well, it all comes down to the subatomic level. Specifically, it's electrons.
Electrons. I thought those are just for electricity.
We usually do think of electrons as just carrying electrical charge, yeah. But they also have this intrinsic property called a magnetic moment.
Okay, hold on. Magnetic moment. That is a piece of jargon I hear thrown around in physics videos all the time, but nobody ever stops to explain what it actually is.
It's true, it gets glossed over a lot.
What exactly is a magnetic moment?
Fair enough. Let's break it down. To put it simply, and keeping in mind this is a highly simplified model of quantum mechanics.
No heavy math today.
Right. You can think of every electron as a tiny spinning top.
Okay, spinning top. Got it.
And because an electron has an electrical charge, that spinning motion essentially creates a microscopic electrical current.
Right. Wait, really? Just by spinning?
Yep. And as we'll explore more deeply later, anytime you have a moving electrical charge, it generates a tiny magnetic field. Always.
Oh, wow.
So that intrinsic little magnetic field produced by the electron's spin, that is its magnetic moment.
I see.
Every single electron is essentially a subatomic bar magnet.
Wait, if every electron is a tiny magnet, and everything in the universe is made of atoms, right?
Right.
Which are completely full of electrons. Shouldn't literally everything be magnetic? Why doesn't my wooden coffee table stick to my refrigerator?
That is the perfect question to ask, and it leads us directly into the source's next principle, which is PS.PHY.5.1.
Okay, what did that one say?
The text states, use models to qualitatively explain the relationship between magnetic domains and magnetism. The answer to your coffee table question lies in that concept right there.
Magnetic domains. Okay, so the text explicitly asks us to use models to qualitatively explain this.
Yes, qualitatively, not quantitatively.
Yeah. Right, so rather than getting bogged down in the quantitative math of quantum physics, which I appreciate. By the way, I was trying to visualize what a magnetic domain actually is.
How did you picture it?
I came up with an analogy. Tell me if this works.
Yeah.
Is explaining magnetic domains sort of like looking at a massive stadium full of people.
I'm intrigued. Let's hear it.
Okay, so imagine an unmagnetized piece of iron. It's like a stadium where every single person in the crowd is pointing their finger in a completely random direction.
Okay, complete chaos.
Exactly, because everyone is pointing differently. There's no overall consensus. There's no single direction the crowd is focusing their energy on.
Right.
But if a leader gets on the loudspeaker and tells everyone to point directly at the stage at the exact same time, suddenly you have this powerful, unified, directional force. All those tiny individual forces add up. Is that what magnetization is?
It's a really good starting point. But to be accurate to how domains actually work in physics, we need to tweak it slightly.
Okay, tweak away.
Your analogy works perfectly for the individual electrons. But a magnetic domain isn't a single electron. It's actually a cluster of atoms.
Oh, okay.
So let's keep your stadium. But instead of individual people pointing randomly, imagine the stadium is divided into large seating sections.
Like section A, section B, section C.
Exactly. Inside section A, every single person is already pointing in the exact same direction. They are completely unified.
Okay.
That section is a magnetic domain, but section A is pointing north, section B is pointing south, and section C is pointing east.
Ah, I see. So the domains themselves are completely magnetized internally, but relative to each other, they're still canceling each other out.
Precisely. In a piece of, say, unmagnetized iron, you have millions of these microscopic domains, each with its own internal magnetic field perfectly aligned.
But pointing all over the place.
Right, pointing in random directions, so the net magnetic field of the whole iron bar is zero.
So magnetizing it is.
Magnetizing the iron isn't about aligning the individual atoms from scratch. It's about forcing all those pre-aligned sections, the domains, to pivot and face the exact same direction.
Wow.
Yeah. When all the domains snap into alignment, their individual magnetic fields combine into one massive macroscopic magnetic field. That is a qualitative model of magnetic domains.
That makes so much sense. And, it also explains why dropping a permanent magnet on the floor can sometimes ruin it.
Oh, absolutely.
You're literally sending a physical shock wave through the metal that shakes some of those domains out of alignment. Like it scrambles the consensus.
That's exactly what happens. The physical impact provides enough energy to break the magnetic alignment of the domains. The sections get jumbled up again.
Okay, so we've established how a static magnet works internally. We have aligned magnetic domains creating a unified field.
Right.
But a fridge magnet is pretty limited. I mean, it just sits there.
Mm.
The really wild stuff, the technology that actually powers the modern world, happens when we introduce electricity into the mix.
That is the big leap.
Yeah. How do we explain an electromagnet? How does adding an electric current change the behavior of these domains?
Well, this is the critical transition point, and the source material addresses it directly in standard PS.PHY.5.2.
The final directive.
Yes. It asks the learner to obtain, evaluate, and communicate information about the relationship between magnetism and electric currents.
And here's where it gets really interesting.
Yeah.
Because the text shifts gears dramatically right here.
How do you mean?
Well, we aren't just sitting back and building qualitative models anymore. The verbs change. We are actively evaluating a dynamic relationship between two seemingly different forces, magnetism and electric currents.
Right. It's a much more active stance.
So what is the bridge between them?
If we connect this to the bigger picture, the bridge is movement.
Movement.
Yeah. Remember earlier when we talked about the magnetic moment?
The spinning top electron.
Exactly. We said that an electron spinning, which is a moving electrical charge, creates a tiny magnetic field. That is the fundamental rule of electromagnetism. Whenever an electrical charge moves, it generates a magnetic field. Always.
So I just run electricity down a standard copper wire.
Right.
That wire is secretly generating a magnetic field around it.
It's not a secret. It is a physical reality. When you switch on a lamp, a current of electrons flows through the copper wire in your wall.
Okay.
As those electrons move, they create a circular magnetic field radiating outward from the wire,
Just from the movement.
just from the movement.
Uh-huh.
Now, a single straight wire only creates a really weak field, but if you take that wire and wrap it into a tight coil, a shape called a solenoid.
Oh, I've seen those in science class.
Right.
Ah.
When you do that, the magnetic fields of all those individual loops overlap and compound.
It's like stacking those stadium sections on top of each other.
Yes. And if you put a piece of iron inside that coil, the intense magnetic field generated by the flowing electricity will force the iron's magnetic domains to snap into perfect alignment.
Wow.
You have instantly created a powerful magnet, an electromagnet.
But the true beauty of an electromagnet is that, well, the second you turn off the electricity, the domains in the iron randomize again, right?
Exactly. The magnetism just vanishes.
That is incredible. We can literally turn a fundamental force of nature on and off with a switch.
And that specific ability is the absolute bedrock of modern engineering.
But wait, let's look at the reverse of this. If running electricity through a wire creates a magnetic field, does moving a magnetic field near a wire create electricity?
It does. It's a process called electromagnetic induction.
Induction, okay.
Yeah, it was discovered by Michael Faraday back in the 1830s.
Okay, I have to push back here for a second because I want to know the actual mechanism.
Sure, let's dig in.
I hear electromagnetic induction, and I get the general concept. Magnet plus wire equals electricity. But how?
The physical cause.
Yeah, what is the physical push? How does moving a chunk of iron near a piece of copper suddenly force electrons to start flowing through a wire to power my entire house?
It all comes down to something called the Lorentz force.
The Lorentz force.
Yes. We know that a magnetic field exerts a physical force on moving electrical charges.
Okay.
Now, think about a copper wire. It is packed full of free electrons just sitting there waiting to move. They're highly conductive.
Right, they're ready to go.
When you take a strong permanent magnet and physically sweep its magnetic field across that copper wire, the magnetic field pushes against those charged electrons.
It physically pushes them.
It physically sweeps them along the wire.
So the magnetic field is acting almost like a physical broom, just sweeping the electrons down the copper pipe.
That is a very apt analogy, actually. The invisible lines of magnetic force brush through the wire, pushing the electrons. And what do we call a flow of electrons down a wire?
We call it an electric current.
Exactly. By physically moving the magnet, you have induced electricity.
That is mind-blowing when you actually visualize it. Just a broom sweeping electrons.
It's beautiful, isn't it?
It really is. And this brings us to the final culminating mandate in the standard. It says to explain the role of magnets in current technology.
The practical application.
Right. The standard demands that we apply this knowledge to the real world. So let's do it. Let's talk about the technology. How are we using this broom of magnetic fields sweeping electrons?
Well, let's start with how you are listening to this right now. You are likely using electricity from a power grid.
Sure.
How is that electricity generated? Whether it's a coal plant, a nuclear plant, or a massive hydroelectric dam, the underlying technology is almost identical.
How so?
They are all just giant machines designed to spin a magnet.
Wait, really? A nuclear power plant is just a really complicated way to spin a magnet.
At its core, yes. In a nuclear plant, splitting atoms creates immense heat, right? That heat boils water into high-pressure steam. That steam pushes against the blades of a massive turbine, causing it to spin.
Okay, I'm with you.
Attached to the shaft of that spinning turbine is a gigantic electromagnet, and it's sitting inside a massive ring of tightly coiled copper wires.
Oh, the solenoid.
Exactly. As the turbine spins, the magnetic field sweeps past the copper wires at high speed, pushing the electrons,
The broom.
the broom. That creates the massive electric current that flows out of the power plant, across the grid, and into your wall outlet. That is what a generator is. It's turning physical motion into electricity using magnets.
Okay, so that's a generator, motion into electricity.
Yeah.
But what about when I plug a fan into the wall to cool off? That's turning electricity back into physical motion.
That is an electric motor, and it operates on the exact inverse principle.
How does that work?
In a motor, you have a coil of wire sitting between two permanent magnets. When you plug the fan in, electricity flows from the wall into the coil.
Okay.
And as we discussed earlier, that current immediately turns the coil into an electromagnet.
Right, because moving electrons create a magnetic field.
Exactly. So now you have a temporary magnet sitting between two permanent magnets.
Oh, I see where this is going.
Right. The magnetic field of the coil pushes against the permanent magnets. North repels north, south repels south.
And that physical repulsion forces the coil to spin.
Yes. We attach a fan blade to that spinning coil and you get a breeze. Electricity turned into motion using magnets.
That is incredibly elegant. The generator at the power plant uses motion to create electricity via magnets, and then the motor in my house uses that exact electricity to create motion via magnets.
It is a perfect, continuous loop of electromagnetism powering our entire civilization.
Wow.
And, the applications go so much further than just spinning things.
Really? Like what?
Think about how we store information.
Like computer hard drives.
Traditional hard disk drives, exactly. They rely entirely on standard PS.PHY.5 magnetic domains.
Wait, really? How does that work?
A hard drive platter is coated in this magnetic material containing billions of tiny magnetic domains.
The stadium section.
It's stadium sections. And there's a tiny, incredibly precise electromagnet called a read-write head. It hovers just microscopic fractions of an inch above the spinning disk.
Don't tell me. Is it flipping the domain?
That's exactly what it's doing.
Oh my God.
By pulsing a tiny electric current, the head creates a micromagnetic field that forces a specific domain on the disk to align either north up or south up.
Binary code.
Yes. North up is read as a binary 1. South up is read as a binary 0.
That is wild.
Every photograph, every document, every piece of software on a traditional hard drive is nothing more than physical patterns of microscopic magnetic domains, all aligned by electric currents.
It's just billions of tiny stadium crowds being told which way to point so I can save a Word document.
Pretty much.
That is unbelievable. And, it brings us right back to the beginning of this deep dive.
The maglev train.
Yeah, I mentioned a maglev train floating in midair. How does that fit into this picture?
Well, maglev, which stands for magnetic levitation, is perhaps the ultimate macroscopic demonstration of this whole framework.
Because it's huge.
Massive. These trains don't have engines on board. The tracks themselves are lined with incredibly powerful electromagnets. By constantly and rapidly changing the direction of the electric current flowing through the track's magnetic poles constantly flip between north and south.
So it's constantly pushing and pulling the train.
Yes. Magnets on the bottom of the train are repelled by magnets on the track, which lifts the 100,000-pound train completely off the ground.
Just floating there.
Right. And at the same time, the alternating electromagnets on the sides of the track continuously pull the train forward and push it from behind. The train basically surfs on an invisible wave of electromagnetic force.
So what does this all mean? We started with 3 brief sentences from a physics standard.
Just a few lines of text.
Yeah. But what it really gave us was a lens. It demanded we start small, explaining the concept of moving electrons in magnetic moments.
Right, getting the foundation.
Then it forced us to build a model, visualizing those clusters of atoms acting as magnetic domains. And finally, it demanded we connect those static domains to the dynamic flow of electric currents.
Revealing the Lorentz force.
Exactly, the sweeping broom that makes generators, hard drives, and maglev trains possible.
It proves that mastering physics isn't just about, memorizing equations. It is about building a conceptual ladder. You can't understand the floating train if you don't first understand how electric currents induce magnetic fields.
Right.
And you can't understand that if you don't first understand what a magnetic domain is. The standard forces you to connect the micro to the macro.
It really does dispel the invisible magic we talked about at the very beginning. It replaces mystery with structural understanding. Which brings me to a final thought I want to leave you with, our listener.
What's that?
Well, this entire source text culminates in a mandate to evaluate and communicate how these forces drive current technology. We just spent this time unmasking the invisible relationship between magnets and electric currents.
We did.
But it makes me wonder, if the ultimate test of understanding our modern world requires us to explain these hidden relationships, what other invisible forces driving our daily lives are we taking completely for granted?
Oh, that's a great point.
Right. Every time you connect to Wi-Fi, every time GPS pinpoints your location from space, even just the gravity keeping your feet on the floor right now, these are all invisible frameworks just waiting to be mapped. What else are we failing to understand simply because we haven't taken the time to stop and build a qualitative model for it?
That is the right question to ask. The world is full of black boxes, but, none of them are truly magic. They are just waiting for the right framework to open them.
They really are. Well, thank you for diving into this with us. We hope this framework gives you a whole new lens through which to view the invisible forces around you, whether it's a fridge magnet or a high-speed train. Keep asking those questions, keep building those models, and we will catch you on the next deep dive.